Welcome back. So now we're going to move on to something which I hope you don't take as me trying to insult your intelligence. Simply, I'm trying to start on something you certainly understand and move on towards inner products. So in front of you is the 2D rectangular coordinate system of the Euclidean space. And we have an arbitrary vector A. And A is a linear combination of the basis states I hat and j hat, and their coefficients are the actual way of getting the linear combinations. Now, what I hope you're familiar with is that we can re-express the a sub x's as follows, and the a sub y's. If you take the scalar dot product of your arbitrary vector with any of your basis states, you'll calculate the associated coefficient. So, I hat dot a is going to give you a sub x, and j hat dot a is going to give you a sub y. And this means we can re-express our arbitrary vector in 2D or 3D space as so. And this is very important to understanding what a wave function is. We've already discussed that quantum operators form eigenvalue equations, but we haven't really discussed the properties of those operators. Now, there's a subset of all the types of operators that could possibly be, and they're known as Hermitian operators. And Hermitian operators have the property that their eigenvalues are real. And obviously, we use operators to measure observables, which have to be real numbers. So that means that operators in quantum mechanics must be Hermitian. So that it might seem that we're trying to constrain all of the possible operators that could possibly be. But in fact, we get a neat trade-off. By definition, Hermitian operators are complete, they are orthogonal, and they are normalized. Now, think about it. So our unit vectors I hat and j hat, let's say, they are normalized to 1, they're unity. They're both mathematically and physically orthogonal to each other, perpendicular to each other, and they're complete because we know we can take a linear combination of them to describe an arbitrary vector in the Euclidean space, which is exactly what's happening at the bottom of your screen here. So, quantum operators must be Hermitian. Hermitian operators are both orthonormal and complete, and this means, and this is very, very important, this means that the eigenstates of Hermitian operators can be used to form a basis for a space. They can be used to describe all of your abstract quantum states, your kets. And we say that the space that abstract quantum states live in is not Euclidean space, but we call it Hilbert space. And the mathematical definitions of orthonormality and completeness are here, but I don't need to get bogged down on those for the moment. So how do we use this completeness in quantum mechanics? Let's take an arbitrary abstract quantum state, ket f. So we want to take a linear combination of basis states in order to express it. Now, those basis states are going to be eigenstates of a particular quantum operator. It doesn't really matter at the moment. We're going to take linear combinations, and these c sub n's are the coefficients on each of the basis states. And these are also known as probability amplitudes. Now, in the same way, if you remember when we tried to take the linear combination of I hat, j hat, and k hat in Euclidean space, this might have been a sub x, this might have been I hat, let's say. But we knew we were able to re-express it using the scalar product. And we're able to do the same thing here, but we use the generalized scalar product, which is known as the inner product. And that's what this quantity is here. So if we have an arbitrary abstract quantum state, and we find eigenstates of a particular quantum operator, then we can take linear combinations of those to describe the abstract or the arbitrary state, and we can find those coefficients using this particular inner product. And remember, these are just numbers. These coefficients, they're just numbers. Now, you might ask, what does an inner product look like when you do it? Though I don't want to get bogged down into it, here are two examples, one of using matrix notation and one of using an integral. Now, the mechanics of it isn't something I'm going to cover in this video. So remember that when we have an arbitrary abstract quantum state like ket psi, and we want to measure the value of an observable associated with a particular operator, well, we operate on the arbitrary ket, but it collapses into an eigenstate of that particular operator, and that allows us to calculate the particular eigenvalues. We know eigenstates associated with Hermitian operators can span our Hilbert space. We also saw the energy, the momentum, and the position eigenvalue equations, each of which involves eigenstates of Hermitian operators. So both ket E sub n, ket phi sub n, and ket x sub n, linear combinations of those can be used to describe an arbitrary abstract quantum state living in Hilbert space. So we would say that when we take linear combinations of the energy eigenstates, we're talking about energy Hilbert space. Here we're talking about momentum Hilbert space, and here we would be talking about position Hilbert space when we take linear combinations of those to describe an abstract or arbitrary abstract quantum state.